You have studied numeric equations like x plus y equals y plus x, and logic equations like x implies y equals not x or y. Now we want to talk about equations using a notation that a computer can interpret automatically. There are many such notations, of course. The one we will discuss is known as ACL2, which is a dialect of a language called Lisp, one of the oldest notations invented for automatic interpretations by computers. We will be using it primarily because it comes with a system of logic that allows us to automate some of the reasoning that can be carried out with software equations using the same rule of inference as before, but with some new kinds of data and new operations. Let's get started by writing down some familiar formulas in the new notation. The conventional notation for the sum of two numbers x and y is x, then a plus sign, then y. But in ACL2, we write the plus sign first, and then the operands. It's known as prefix notation since the operator comes first, and the parentheses around it are required. X implies y, the logic notation with the arrow, is written parenthesis implies, that's the operator name, and the operands x and y, and then a closing parenthesis. A formula with two operators in it, well, it's the OR. This operation is the OR of the negation of x and y, and again the operators come before the operands with parentheses required. Even equations in ACL2 take on the prefix syntax. So for example, if we want to write an equation x implies y equals not x or y, we write the equals sign first after a parenthesis, then the first operand, the left-hand side of the equals sign, and then the right-hand side of the equals sign, all in this prefix ACL2 notation. And that means this formula in ACL2 means the same thing as this equation in logic. Numeric equations conform to the prefix rule 2. So we have plus xy plus yx with an equation between them, and ACL2 is written like this, and conventionally we would write it like this. Like implies the not, the equal operator delivers a Boolean value, that is a true-false value. The equation equal plus xy plus yx, of course, is true. That's the expression of the commutativity equation for addition. And when we write an equation like that, we expect the value to be true. When we write an equation, write an equality between the sum of 2 and 3 and the sum of 3 and 4, of course that's false, and we would expect the equals operator to deliver false in that case. So equal in ACL2 is a Boolean operator. It delivers true or false based on a comparison between its operands. The ProofPad system is a piece of software that interprets ACL2 formulas. If we ask ProofPad to compute the value of the formula equal plus 2, 3 plus 3, 4, it would respond nil. Nil is the ACL2 symbol for false. On the other hand, the ProofPad response to equal plus 2, 3 plus 3, 2 would be T for true. And this equation is a special case of the commutativity equation for addition. How about the commutativity property in general, which we know to be true? Equal plus xy plus yx. If we enter that into ProofPad, the ProofPad system, it responds with an error message. That's because ProofPad requires specific values for the operands of its operators, not general purpose values like x and y. If we wanted to check general equations, we have to give it some values to use, and one way to do that is to define a property, def property in ProofPad, give a name for the property, and then specify a range of values, of random values for the variables to take. So this says that x is supposed to be a random integer and y is supposed to be a random integer. And put together a collection of random integers and check this equation for each of those. That's what this property says to do. If we enter that property into ProofPad, it responds with a greening of the area called the status bar on the screen. So when you define a property and the status bar turns green, you know that ProofPad has run the test against some random values in the specified ranges, and all of those tests have passed. All the formulas come out to be true in every case. We want to do this for operations other than logic operations or numeric operations, and for that we'll need some more axioms to define new operators. One of the operators we're going to talk about is cons. That's construction of lists, and it's actually an insertion operation. So if you have a list, which we denote with square brackets like this, so we got square brackets around the outside delimiting the ends of the list, and then the various elements of the list are written in order inside. Here I've got them named x1, x2, and so on up to xn. The list is the second operand of this construction operation. The first operand is the new value to be inserted, and the value it delivers, the value that this construction operation constructs, is a list that's like the second operand, but with the first operand inserted in the first position. We have two other operators we want to talk about at this point. One, and both of those are ways to deconstruct lists. So if you have a list, it starts with the element x0. If you apply the first operation to it, it delivers that first element. If you apply the rest operation to the same list, what you get back is the list, but without its first element. Our convention here is that n, in our subscripting here, is a natural number, that is a whole number of 0 or greater. So in this list, x1 through xn, n tells you the number of elements in the list. In this list, of course, there would be n plus 1 elements because there's an extra subscript in there. So this list has n elements in it. We're allowing n to be 0, which would be 0 elements. In that case, there would be no elements written in between. It would just be left bracket, right bracket, and that would be the list with no elements, or the also called the empty list. The ACL2 name for the empty list is nil. So nil stands for the empty list, and it also, as you know, stands for the value false. So it's interpreted as a true-false value, namely false if it's in a Boolean context, and as an empty list if it's in a list context. We can reason with software equations in the same way that we reason with logic equations and numeric equations. For example, the formula first of cons of x0 and the list x1, x2, x3, if we apply the cons axiom, we see that the list we get when we insert x0 into x1, x2, x3 is just x1, x2, x0, x1, x2, x3. And if we pull the first element out of that according to the first axiom, we just get the first element. So that's, in this case, x0. Here's another example. Here we have a more complicated formula with 3 applications of the cons operation. In this one, the last application, it inserts x2, the value x2, into an empty list. And if you look at the cons axiom, it says that if you insert an element into an empty list, that is, there are no elements in between, you just get a list with that single element and no other elements in it. So the value of that list is just the list consisting of the element x2. Now if we insert x1 into that list and look at the cons axiom again, we see that we get the list consisting of x1, x2. And again, if we're going to do a cons operation with x0 as the first operand and this list is the second operand, we get the list of 3 elements written here. And we applied the cons axiom in all 3 of those cases. In reasoning about software equations, we will use the first and rest axioms either in this form with lots of subscripts, or in this form where the pattern on the left is a first of a constructed list where you insert a new element, and the value you get back when you apply first to such a list is just the element which is the first operand of the cons. And when you apply rest to such a list, you get back the second operand of the cons, which is the list that's being inserted into. So this form of the first and rex axioms and this form of the first and rex axioms, they're equivalent, they mean the same thing, and we'll apply whichever one is relevant in our particular situation as we go along. So the most important takeaway from this discussion is that we're applying the same rule of inference and this same matching of patterns and formulas and equations that we were using to reason about numeric operations and formulas using Boolean operations.